Narrative imagining and story is the fundamental instrument of thought. Rational capacities depend upon it. It is our chief means of looking into the future, or predicting, of planning, and of explaining. This is how Mark Turner rationalizes the power of story. However, mathematics has largely missed out on stories to thread logic and concepts for best educational outcomes. Human brains are so hardwired for stories that mathematics has to take this route to ensure no child left behind in mathematics. To me, storified mathematics is the first step towards mathematizing thinking. Here is our first presentation of a storified mathematics, secondary level trigonometry. Among secondary students, triangles and trigonometry are problematic for the best, and which is why we chose trigonometry to showcase how a well-narrated, logically tight exposition can work wonders. I personally look forward to hearing if this reel helped you understand the origin and raison d'etre of trigonometry. Of course, this reel uses an alternate logical connection and aims at foundational conceptual clarity, not computational skills. First and foremost, we need to appreciate the uniqueness of triangles. Most notable is the infiniteness of triangular shapes, compared to one-shaped figures such as square, circles, rhombuses, regular pentagons, etc., or the two-shaped rectangles. Circle, square, etc. are just bigger or smaller of same shape. Relevantly, it is much easier to develop universal formulas for geometric properties of same-shaped figures, such as square and circle, but near impossible for the infinite-shaped triangles. Thus, theoretically, every triangle could be a mathematical challenge. How do we know anything about the length of its sides and the measure of its angles? Except by discretely measuring the three sides and the three angles of all triangles. But that is too much to expect for something that is infinitely divergent. And triangles would lose mathematical applications if we could not develop a quantifiable relationship among sides and angles that is true for all triangles. Trigonometry became the domain of mathematics to investigate and find way and means by which we study triangles, to find something common across all triangles. Trigonometry literally means knowledge of the relationship between the sides and angles of triangles. There is more why trigonometry is important. They are the simplest of the polygons, three-sided polygons. Recall, polygons are closed figures made with straight lines. No wonder triangles are the molecules of all other polygons, regular as well as irregular. These polygons can be seen as sum of triangles. And in turn, all the infinite kinds of triangles can be seen as the sum of two right triangles. Thus, right triangles are the atoms of all polygons. Thinking the general relationship of sides and angles, there is a good news. Despite the uncountable diversity in the measures of angles and sides, the angles and sides of triangles bear a relationship. For example, the length of a side opposite to an angle increases as the angle increases. But this relationship is not universal, and the picture shows this. There is a relationship that holds for all triangles. The smallest side is opposite the smallest angle, and the largest side is opposite the largest angle. But this relationship is not quantifiable. That is, it does not boil down to numbers, such as if the smallest angle is x degrees, the opposite side will be of y length. Because this relationship is not quantifiable, it is not mathematically valuable. Long story short, it was discovered that while there is no definite relationship among sides and angles of all triangles, a particular kind of triangles show abiding relationship among angles and sides. In right triangles, there is a universal relationship between sides and angles. The two of the non-right acute variable angles and the different ratio of length of sides bear an enduring relationship. So even in right triangles, it is not the length of sides, but the ratio of length of sides bore a relationship with the two varying angles of right triangles. The relationship in right triangles implies two things. First, a given angle retains the same specific ratio of length of sides, whatever the triangle size. Second, a change in angle measure would result in change in the ratio of the length of sides. This is a great discovery because each angle measure will always have a definite ratio of sides. Thus, if we know an angle in a right triangle, we know the ratio of its sides. And then, mathematically, we just need to know the actual length of just one side, to know the actual length of all the sides. This is to say, in right triangles, if we just know one angle and length of one side, we can know all the three sides and angles. And this is all we need. This was a great news about triangles, because what is applicable to all right triangles is applicable to all triangles, because all triangles can be seen as two right triangles. Thus, we can know about the sides and angles of any triangle by knowing all about the sides and angles of each of the two right triangles in it. Next, we will animate to show how the change in the side lengths does not change the ratio of the sides for a given angle in a right triangle. The animation is to show the steady relationship of the ratio of length of sides and a given angle. There are three unique ratios of the sides in a triangle. In the animation, we can see that, for a given angle, the ratio of the length of the corresponding sides does not change, even as the length of the sides changes. Each of the two non-right angle has a definite relationship to each of the three ratio of sides. Thus, for a given angle measure, the ratio of length of sides of a right triangle is the same for all right triangles with the same angle measures. Expectedly, this definite relationship of the measures of angles and ratio of sides in right triangles is the foundation of trigonometry. And in mathematics, we have a name for it. Functions are a kind of relations where the relationship outcomes are definite. By definite, it is meant that an angle will always have the same value of the ratio of sides. Next, we only have to see the quantitative nature of this relationship. Obviously, functions that quantify sides and angles relationship are called trigonometric functions. A function maps each input to exactly one output, and the inverse function reverses this process, mapping each output back to its original input if such a reverse mapping exists. A trigonometric function relates an angle of a right triangle to the ratios of its sides. An inverse trigonometric function reverses this process, determining the angle that corresponds to a given trigonometric ratio. Let us now get real about the ratios of length of sides and the angles of right-angled triangles. We will pick a right-angled triangle and see for ourselves the ratios and the two acute angles. As shown in the picture, for the triangle ABC, the three primary ratios of sides are side A by side C, side B by side C, and side A by side B. There are three more ratios, the multiplicative inverses or reciprocals of the three primary ratios. They are side C by side A, side C by side B, side B by side A. So there are three unique ratios and three non-unique inverse ratios of the three sides. And the two angles that can vary in a right-angle triangle are angle A and angle B. We do not consider the angle C for relating it to the ratios, because it will always be 90 degrees if triangle ABC has to continue to be right-angled triangle at angle C. To be clear, angle C also has related ratios, but it is of little mathematical interest because the ratios would not be changing due to any change in angle C. All changes in ratios of sides will be due to the changes in angle A and angle B. Geometrically, the individual sides do not bear the same relationship with both the two acute angles. For instance, side A is away, opposite, to angle A, but it is next, adjacent, to angle B. Thus, if being opposite and being next have any geometric significance, then the ratio side A by side C would be different in meaning for angle A and angle B. There is indeed a geometric significance in a side being opposite or being next and adjacent to an angle. An opposite side is not an arm for an angle, but an adjacent side is an arm. Every angle needs two arms to exist. By default, for an angle, the pair of sides that are its arms are specific to that angle. Naturally, the six ratios will be different for each of the acute angles, when viewed from the perspective of the angles in terms of adjacent or opposite sides. Next, we will see how exactly this adjacent and opposite sides difference creates mathematical difference. Three primary ratios have names, unique identities. At this level of understanding, the genesis of the names is not important. Sine, cosine, and tangent are just names of functions that take angle as input and output an appropriate ratio of sides. Here is all the functions and ratios in a summary. Sine is a primary trigonometric function of angle P, which gives the ratio of sides as O by H. Cosecant is the multiplicative inverse trigonometric function of sine, which gives the reciprocal of ratio of sides, that is H by O. Cosine is a primary trigonometric function of angle P, which gives the ratio of sides as A by H. Secant is the multiplicative inverse trigonometric function of cosine, which gives the reciprocal of ratio of sides, that is H by A. Tangent is a primary trigonometric function of angle P, which gives the ratio of sides as O by A. Cotangent is the multiplicative inverse trigonometric function of tangent, which gives the reciprocal of ratio of sides, that is A by O. Thank you. With us, you will master all the mathematics you need. Be good to you, not just others.